Hello, Eastview Scholars, and welcome to this edition of Sharp Shorts, where we're going to work our way through theories of the atomic model. We're not going to go all the way through this timeline. We'll go up to about Rutherford, where Rutherford came up with the first significant proof and changed the theory of the atom structure to what it is today, or more of what it is today. And in doing so, we hope to do two things. One, give you a better visual of give you something in your head, so as we talk about atoms and things that you can't see and how they interact with the air and how they bond and how they do reactions and how the electrons are involved in that you can really get an understanding of that from the basics on up. And it's a great view of scientific method and change in technology. Anyhow, it starts with Democritus, and really the only thing we're going to point out here is Democritus gave us the word. Basically, if you remember the movie and the noodle guy that was making the noodles and making them smaller, smaller, and smaller, he just said, if I take a piece of matter and have it 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 and keep going until I can't have it anymore, I'll have the smallest functional unit of that, and I'm going to call that an atom. This small solid piece of matter that makes all other matter. That was really it. Now, Greeks were great at philosophy. They weren't great at experimentation, so you had a large gap of years here. And really then through that you could experiment, and people did experiment with the earth and learn things and start naming elements, etc., etc. And through all their theories, they came up with what Dalton used as his foundation to say, hey, matter is made up of atoms, and this is what, it is this small solid piece of matter, and here's what it does. It gave you a working thing of that. He based it on these three laws. Now in science, most everything is theory, because theory is always adapting, changing. You find new things, and technology advances, and things change. It takes a lot to become a law, which means that's absolutely true. But these are absolutely true. The law of conservation of mass, and it's actually the law of conservation of mass and energy, says you cannot create or destroy matter or energy. Basically what's here is here. What you start with is what you got. How was that proven? The simplest way was in every chemical reaction. If you do it in a closed system, and you take the total mass of the reactants you start with, and you trap all the products that come out, doesn't matter what phase they might have changed to or anything else, those masses are always equal. And you will discover that in lab. That is true. Do it over and over and over again. Don't lose any products. The mass. So really what you're saying, and what Dalton was kind of saying then, or believed that meant, among many other things, was, hey, wait a minute. So really a chemical reaction is just a rearrangement of matter in some form. I'm putting stuff together, I'm taking stuff apart, I'm rearranging it. The second one is, as you discovered what compounds and things were made of, turns out they always had definite proportions, or I like the word composition here over proportions. I would maybe say the law of definite composition. All that meant was those compounds always had the same formula. Water is water is water. Water is always two hydrogens, one oxygen. No matter where you find it, it's always two hydrogens, one oxygen. Sodium chloride table salt is always one sodium, one chlorine. Pretty straightforward. Law of multiple proportions really comes down to this. You only have 92 naturally occurring elements, and you have billions of compounds. You are going to have compounds that are made out of the same stuff that are different. Water and hydrogen peroxide. Notice that they're both made of hydrogen and oxygen, but the oxygens are in a 1-to-2 ratio. The hydrogens are 1-to-1, but the oxygens are 1-to-2. And so the law of multiple proportions just said, if you have two compounds that are made up of the same elements, you will have some set definite proportion as you compare those elements. There you go. What Dalton used that for, though, was to say, hey, this is a working model of what the atom is. And I'm going to tell you this. Matter, all elements are composed of indivisible little particles we're going to call atoms. Really not a change from Democritus. The smallest solid little piece of thing I can get. And that's the key word, solid. Okay. That's different than what we know today. but solid is this indivisible little particle. Atoms of the same elements are the same, so copper is always copper is always copper. Atoms of different elements are different, so copper atoms are not the same as zinc elements. Okay? Atoms mixed together in whole number ratios, H2O for water, NaCl for sodium chloride. Absolutely. And therefore chemical reactions occur when atoms combine, separate, or rearrange. You can make something, you can break something, you can rearrange something. And an astounding ability to take those laws and say, wait a minute, if I can't create or destroy energy or matter, and these compounds always have the same composition, and compounds made of the same things have a set proportion, and then what I'm looking at is matter is made up of atoms. These atoms are these small solid little particles like Democritus said, and this is how they operate. For somebody who had no technology, no ability, of course no knowledge that there were protons, neutrons, electrons, no ability to find that out, no belief that there were those parts, that the atom, the smallest, divide till they can't anymore, smallest piece of that functional matter is the atom. Everything here is basically correct. Yes, you can divide an atom today, but it's not a natural occurrence that happens for us. It's something we have to do. No, he didn't know neutrons, so he didn't understand that there were isotopes, but really isotopes are just different forms of the same element. So that's true. Absolutely different ones are different. We know this is absolutely true. We know this is absolutely true. So for a guy basically having a closed, I can't open it, I can't x-ray it, I can't do anything with it shoebox, trying to shake it and figure out what's inside, he did a pretty darn good job. Okay? That gets us to Thomson. Notice the timeline in the span of years, so there's going to be more technology. Thomson's claim to fame, I'm going to tell you right now, was discovering the electron and discovering that it was about 2,000 times less than a proton. Now, let's not get confused. Dalton did not discover a proton. He did not even know about protons. He was of the belief that the atom was a positive mass with these electrons stuck in it. But he did discover the electrons and get the size of their mass. And that was because the hydrogen atom, as you know, was one proton, one electron, no neutrons. He didn't know that, but he knew that it was the smallest one and was able to determine the mass off of that. Anyhow, here's what a cathode ray tube was. It's the basis of old TVs and monitors. It's a vacuum-sealed gas. This is a tube, like a glass tube. Suck all the air out of it, put an inert gas in there. I have a negative portion of plate, a positive plate. I have a battery or an electricity supply. When I turn it on, I'm going to get this beam of light as I excite those electrons in the gas, and it's going to go straight across to the positive pole. Don't mind the curve yet. That's part of his experiment. In trying to understand electricity and stumbling upon the electron, he devised this experiment where he took these magnets. Basically, that's what these were, a positive, negative magnet. And every time he fired on the tube and the light went on, the light bent towards the positive one, which meant that something in that particle was negative. Okay? He also did an experiment where he was able to switch it around so that the beam of light would activate from positive to negative, and the same thing would happen. So he was able to say, hey, there's also some amount of charge, just the opposite sign, in some of these particles. So how he put that together was what he called the plum pudding model, because he was British, and plum pudding is this bready stuff with plums jammed in it. Call it the blueberry muffin model. Now, key is still solid atom. What the atom is the solid positive mass with these plum pudding, with these blueberries stuck in it, evenly distributed to have a neutral atom. Same amount of electrons as positive charges, but the cakey part of the muffin was positive, the blueberries are negative till they're even, and I'm calling it the plum pudding model. Okay? Which gets us to Rutherford, basically his lab assistant who designed an experiment, one of the most famous To prove the plum pudding model, they took gold, they hammered it as thin as you can, because that's what gold does. They surrounded it with basically what is a photographic screen. They had this radioactive source that would shoot out these positive alpha particles. The hypothesis is that because this was so thin, and those atoms, those plum pudding atoms, would be evenly distributed, that this tiny, tiny little alpha particle, smaller than the atom, would just pass straight through and go straight through. Which it didn't. As you can see by the experiment, there were deflections. And some major deflections also. Rutherford's quote was, "It was as if you shot a cannon at a piece of tissue paper and it bounced back." But what it meant was the plum pudding model was not correct. Rutherford discovered the nucleus. He said you have to have this nucleus that is small, densely packed, really a very almost insignificant portion of the whole volume of the atom, but all the mass of the atom. And that positive charge is in there. Again, the proton wasn't here yet, but just a small positive mass with these electrons not as a part of that mass, out in the rest of that volume. He didn't know what to do with them, so he said that they rotated the nucleus like planets around the sun. But the big jump here was that the atom is not solid. The atom is mainly empty space, and you have this solid positive nucleus. That was a huge jump and leap towards our modern theory. So in our next series, we'll go from Rutherford through the modern quantum mechanical model, put it all together. Until that point, Scholar on, Eastview.